Hello, welcome to a video about wave-particle duality. Here are a couple of artistic representations of the dual wave and particle nature of light. So I'll start off with the learning intention for this video. In interacting with matter, light behaves like particles, called photons, with energy given by energy equals h frequency, or h times frequency, and momentum given by momentum equals h divided by lambda, or a wavelength. H is Planck's constant. It's a number that never changes. It's 6.63 by 10 to the negative 34. Obviously, F is frequency of light and lambda is wavelength. To be successful in stage 2 physics, it's expected that you're able to calculate the energy and momentum of photons in various regions of the electromagnetic spectrum. So before we continue, it is helpful to remember when we're discussing wave-particle duality that light isn't easily comparable with other physical phenomena, and it exhibits characteristics of multiple models. When we're talking about models, these are like analogies that we use to describe the universe, but we could be wrong for all we know, but the results of experiments lead us to believe that the analogies that we're using are correct. So for example, with Young's double slit experiment, we observe interference that occurs with the light involved in Young's double slit experiment. So we'd say that, well, this is exhibiting wave-like properties, so light must be a wave. However, in other experiments that are conducted, which we'll look at down the track, so the photoelectric effect, this could only be explained by light being a particle, so light's exhibiting particle-like properties in these types of experiments. So perhaps light is something that we, in our tiny human minds, can't quite fully comprehend. Maybe it literally is just a wave and a particle, and we have to accept that it is both, or it's something completely different that has wave-like properties and particle-like properties. But for the moment and time being in the field, it's accepted to just say that light has a wave-particle duality. Interestingly, de Broglie, whose work we'll look at again later on, hypothesised that all matter has a wave-like nature. So if light has a particle nature, or if waves have a particle nature, then perhaps all matter has a wave-like nature, and this is true for electrons. And we'll explore this later on. Here is a meme to represent the wave-particle duality of light. An equation that we'll be using in this section is the energy of a photon equation, and this is called Planck's equation. Planck and co. were studying the spectrum of light emitted by hot objects, and they noticed some features that couldn't be explained by the wave model, and their solution was to assume that light was emitted as photons, which are discrete quantized packets of energy. The energy of a photon is equal to Planck's constant, which is always 6.63 by 10 to the negative 34 joule seconds. It's equal to this multiplied by the frequency of a wave, or it's also equal to Planck's constant multiplied by the speed of light divided by the wavelength of the given light. And this is and this makes perfect sense if you recall that the speed of light, which is equal to 3.0 by 10 to the 8, is equal to the frequency multiplied by the wavelength. So therefore frequency must be equal to c divided by wavelength, or divided by lambda. So for all electromagnetic light waves, or all electromagnetic waves, frequency is going to be equal to the speed of light divided by lambda. So maybe you can see in this equation here, c on lambda is equal to the frequency, so it's just in place of the frequency. Something worth remembering that we touched on last term is that 1 electron volt is equal to 1.6 by 10 to the negative 19 joules. So you might need to convert between electron volts and joules, because often photons are measured in terms of electron volts, or the energy of photons are described in terms of electron volts. However, you'll need to be converting to joules to use Planck's equation, because Planck's constant is in terms of joule seconds. So first example, calculate the energy in joules of a photon with a wavelength of 833 nanometers. So to do this, we'll crack out Planck's equation. E is equal to h multiplied by frequency. We actually don't know what the frequency is, but we do know what the wavelength is. So I'm going to go ahead and use hc divided by wavelength. We know that the wavelength is equal to 833 nanometers, so 833 by 10 to the negative 9 meters. We know that c is equal to 3.0 by 10 to the 8 meters per second, and we know that h, which you'll be given on your formula sheet, is equal to 6.63 by 10 to the negative 34 joule seconds. So that is Planck's constant. We can then go ahead and use this equation. So E is going to be equal to 6.63 by 10 to the negative 34 joule seconds, and then multiplied by 3 by 10 to the 8 meters per second, divided by the wavelength, which is 833 by 10 to the negative 9 meters. Pop all of that in your calculator, and the energy in joules of a photon with a wavelength of 833 nanometers is going to be equal to 2.39 by 10 to the negative 19 joules. In our next example, a photon of UV light has an energy of 8.3 electron volts, and we need to calculate its frequency. So the first thing that we're going to do here is convert the energy into joules, because that's what we'll need to work with when we inevitably use Planck's equation to calculate the frequency of this photon. So first of all, 8.3 electron volts is going to be equal to 8.3 by 1.6 by 10 to the negative 19 joules. Sorry, a bit of a wonky J there. I'll fix that up. There we go. And this is going to be equal to 1.328 by 10 to the negative 18 joules. So that's how many joules we have if we've got 8.3 electron volts. Next, we're going to use our Planck's equation. E energy is equal to Planck's constant multiplied by frequency. We've got the energy, we know that it's 1.328 by 10 to the negative 18, and h is going to be equal to Planck's constant, which is 6.63 by 10 to the negative 34 joule seconds. You'll have that on your formula sheet. We'll rearrange this equation so that frequency is the subject, so frequency is going to be equal to energy divided by Planck's constant. So we'll be doing 1.328 by 10 to the negative 18 joules divided by 6.63 by 10 to the negative 34. And our frequency, if you pop that into your calculator, is going to be 2.0 by 10 to the 15 hertz. Another example, we've got a 50 kilowatt radio transmitter that emits tele signals with a frequency of 0.91 gigahertz. Calculate the number of radio wave photons emitted by the antenna each second. So this problem requires a little bit more previous or prerequisite knowledge. So for this one you need to remember that power, which is what we're given here, so 50 kilowatts is a power, is an amount of power. Power is equal to the change in energy divided by the time over which that change in energy occurs. And that change in energy is going to be equal to the number of photons multiplied by the energy of each photon, which is going to be equal to Planck's constant multiplied by the frequency of each photon, and then divided by t, which is the time. I'll rewrite this, so we've got power is equal to nh frequency over t. Because we're talking about the antenna each second, t is going to be equal to 1. So we therefore end up with P is equal to n, which is the number of photons emitted, multiplied by the energy of those photons, which is h multiplied by frequency, so Planck's constant multiplied by frequency. If we want to get n by itself, we'll just divide both sides by the energy, which is Planck's constant, and multiplied by frequency. Hopefully you can see I've just brought the n or flipped the equation around so that n is on my left hand side. So in order to determine the number of photons emitted by the antenna each second, we just have to substitute our power, which is 50 kilowatts, so 50 by 10 to the 3 watts, and our frequency, which is 0.91 by 10 to the 9 hertz, and h will be 6.63 by 10 to the negative 34. So sub all of this in, 50 by 10 to the 3 divided by 6.63 by 10 to the negative 34 multiplied by 0.91 by 10 to the 9 hertz, and the number of photons each second being emitted will be equal to 8.29 by 10 to the 28. So 8.29 by 10 to the 28 photons per second. Alright, so now we'll take a look at photon momentum. Originally it was thought that electromagnetic radiation caused electrons to vibrate with the same frequency, and then emit electromagnetic radiation with the same frequency. However, Compton conducted an experiment with X-rays and graphite. Graphite has loads of free electrons, and he found that the wavelength of scattered X-rays was longer than the wavelength of incident X-rays. So the scattered X-rays had a lower frequency and hence a lower energy. So if they've got a longer wavelength, that means that their frequency is lower, and frequency corresponds with energy directly, so lower frequency therefore means lower energy. So Compton deduced from this that the X-rays must be behaving as particles, so photons, and that they were transferring their energy and their momentum when they hit electrons. So this scattering was known as Compton scattering, and this is what, I guess, another example of an experiment that highlighted the particle nature of light. So we've got an incident photon coming in here. It's hitting an electron. The electron is scattered and the photon is also scattered, and hopefully you can see that the wavelength of the scattered photon is much longer, the frequency is much shorter, so the photon has reduced energy. So that original theory that electromagnetic radiation induced electrons to vibrate with the same frequency and then emit electromagnetic radiation with the same frequency was shown to not be the case. Compton used Planck's formula as well as Einstein's theory of special relativity to derive his equation. So if we start off with Planck's formula, energy of a photon is equal to Planck's constant multiplied by frequency. We can then use relativity and say that energy is equal to mc squared, and that will be equal to Planck's constant multiplied by the speed of light divided by wavelength. We can then cancel 1c on each side, or divide both sides by a c, and we'll end up with mc, so mass times the speed of light is equal to Planck's constant divided by lambda, and we know that momentum is equal to mass times velocity. This here is mass times velocity, it's just mass times the speed of light, or mass times the velocity of light. So we end up with this equation here, P, or momentum, equals Planck's constant divided by lambda. So some examples. What is the momentum of a photon of red light with a wavelength of 650 nanometers? So to work this out, we just use our equation, momentum equals Planck's constant divided by wavelength. We know that a wavelength is equal to 650 by 10 to the negative 9 meters, and that Planck's constant is equal to 6.63 by 10 to the negative 34. So P equals 6.63 by 10 to the negative 34 divided by 650 by 10 to the negative 9. Therefore, momentum is going to be equal to 1.02 by 10 to the negative 27, and our unit for momentum is kilogram meters per second. In the next example, we've got an excited magnesium-24 nucleus which undergoes gamma decay, emitting a photon with an energy of 2.76 megaelectron volts. What is the momentum of the gamma ray photon? So to do this, first thing that we'll do is convert this quantity, 2.76 megaelectron volts, 2.76 to joules. So if we've got 2.76 megaelectron volts, this is equal to 2.76 by 10 to the 6 electron volts. And we can multiply this by 1.6 by 10 to the negative 19, and this will be 4.416 by 10 to the negative 13 joules. The next thing we'll do is we'll say that momentum is equal to Planck's constant divided by lambda. And what we're also going to recognise is that energy is equal to hc lambda. Therefore, lambda must be equal to hc divided by energy. So if lambda is equal to hc divided by energy, and we sub this into where we see lambda, then momentum must also be equal to h divided by hc divided by E, or energy, which is equal to h energy divided by hc. The h's are going to cancel out, and we'll be left with momentum is equal to energy divided by the speed of light. So if we sub our energy value in, make sure it's in joules, 4.416 by 10 to the negative 13 joules divided by 3.0 by 10 to the to the 8 meters per second, then our momentum for the gamma ray photon is going to be equal to 1.47 by 10 to the negative 21 kilogram meters per second. Some further evidence for the particle nature of light include some old school photos and how they were produced. So if old school photos were produced with different intensities of light, reducing the intensity would, I guess, make the image appear kind of like pixelated. So the image would become a collection of dots, or the fact that the image was made up of a collection of dots would become apparent at these reduced intensities. And this suggests or implies that the image is produced by the arrival of photons at a detector. If the image was produced with a wave and the intensity was reduced, the overall image would still be there, but it would just be dimmer, but it would still be complete. So the fact that the image becomes incomplete with these old school like camera detector thingies, the fact that the image becomes incomplete at reduced intensities suggests or is evidence for the particle nature of light. Another example of evidence for the particle nature of light is, interestingly, the double slit experiment, but with different light intensities. So the double slit experiment is an example of the wave nature of light with the light and dark fringes that occur. but by adjusting the intensity of the light used in the double slit experiment, the particle nature of light becomes evident. Eventually, if you've reduced the intensity enough, there'll be no discernible fringes that occur, and these only become apparent as you increase the intensity again over time. So perhaps you can see in around these bottom images here, the fringes are quite obvious, but in these, particularly this early one here, it just looks random, like the dots are just kind of rocking up on the screen wherever, and the fringes only become apparent as the intensity increases. So this demonstrates a particle-like interaction, but it's not classic behaviour for a particle because as the intensity increases, a wave-like interference fringe is produced. So this is kind of an example of both, and it's definitely an example of the dual nature of light, or the dual wave particle duality of light.